Okay, so we're going to go to optimizing surface area and volume. Okay, so we're production managers and we're designing a toy case for babies. So this is going to hold things. Our production company can only afford 900 centimeters squared of material for each toy. Okay, so because it's squared, essentially what they're telling us is that's the surface area of the object. And normally if we're talking about a case, maybe like a chest or something to hold toys, we're thinking about it's usually known as a rectangular prism, right? If I'm going to build a case, my rectangular prism is probably my best shape. That should be like that. My best shape to use. Right? We have a chest. Now, what type of rectangular prism is the question? If you're going to build a case for something, you want to be able to optimize the volume of this case. Right? If you're going to sell it, you want it to hold as much material as possible if you're going to sell it properly. So what we have to figure out is what dimensions will optimize our volume being the space it takes up inside. So from our area and perimeter, who remembers what is the most efficient four-sided shape? A square. Okay, so if we have a square face on this, we could have a square face prism, which is usually known as a rectangular prism. How can we apply this idea to a three-dimensional shape? What shape would be three-dimensional like a square? What do we call it? A cube. Okay, so in other words, a cube is the best prism for holding volume. Okay, in other words, all of the sides are an identical length. So if we have a restraint on the amount of material to build this case, building a cube for a prism will be the most efficient. Now, we did learn there was more efficient than four-sided shapes. What was the most efficient shape? A circle. We knew a circle was the most efficient shape. If we were to take this idea into three-dimensional, what would we be talking about? That's right. A sphere would actually be best, and I'm going to try my best here to give us a sphere. Does that kind of look like a sphere? A little bit? Okay, so technically this is the best shape, and we'll actually get into seeing how much better this would be. Now, as being a case for putting things in, we know in reality this might not be best because our case would probably roll all over the house. And if we want to stay in one spot, that's probably a better shape. So let's get into the math involved. We have a cube. Okay. So they've given us surface area. We know surface area of the cube, because we're constrained, is 900 centimeters squared. Okay, so if we're constrained, what is the surface area of a cube? Does anyone know the formula for it? It should be in your agendas there. Surface area of a cube.
6s squared.
That's perfect. Okay, so the formula for the surface area of a cube is 6s squared. And essentially what it is because if we're talking about surface area, we'll call this a side and this a side. The sides are the same, okay? So we multiply the two sides by each other. That's s times s, which is how we get our s squared. And there is 1, 2, 3, and then at the back 4, 5, and underneath 6. There are 6 sides to it. So we take that one surface area and we multiply it by 6. That's how they built this formula. Okay? Now we know the surface area, because of our constraint, is 900. So we're going to replace it with the number 900 is equal to 6s squared. And we want to isolate for our variable s. That's right. So we're going to divide both sides by 6. Okay? That will leave us with s squared on this side. What is 900 divided by 6? What is it? 150. Beautiful. Okay, so we still haven't isolated for s. In order to get s by itself, we need to root, or square root to be specific, because it's a power of 2. We need to square root both sides. So we have s and the square root of 150. Kieran, can you do that in your head? Ooh, good, eh? 12.24. Very good. Good estimate.
I thought that was a church.
That was awesome. Okay, so 12.24. Did I give us a unit of measurement? Yes, centimeters. So each of the sides of our cube needs to be 12.24 centimeters in length. So if that's our measurement in length, let's find out the volume of this cube. What is the formula for the volume of a cube? And the surface area. That's right. Because it's a prism, it's just length times width times height, but it can be simplified. Are the length, the width, and the height, what's the special relationship between them all? It's not that they're each cubed. They're all what? They're all the same. So let's refer to it as side. Because all the sides are the same, it's the same as writing side times side, which is s cubed. Good. We know that the side length is 12.24, so our volume of our cube is going to be 12.24 cubed. I can't imagine you can do that one. If you can, you're the best.
I probably could have been.
It would take a while. Okay, 1,837. 1,837, approximately, and that's centimeters cubed. So that would be the volume. In other words, with a prism, our max amount of volume. Now, let's say that the company didn't care that our case stayed still. They just wanted us to maximize our volume. Well, we would know that a sphere would be best. So let's do the same idea with a sphere. Go into your agendas, because you guys have the formula there. Surface area of a sphere is 4, pi r squared. Okay? So, the radius, now this is a hard idea, but think about being from the middle of the sphere to the outside of the sphere, is the radius of a sphere. Okay? So, the radius is really the only variable, because remember, pi is actually a number. So there's only one variable in here, the radius. We need to figure out what radius of a sphere we can make when our surface area is constrained. We're still constrained at 900 centimeters squared. So we're going to replace our surface area with 900 is equal to 4 pi r squared. So we'll do this one step at a time. Let's say we want to move the 4 at first. To move the 4, we divide both sides by 4. We cancel out here. On the right, we'll be left with pi r squared. Our 900, 225. All right, we're taking your word. 225. Okay. Excuse me. So, 225 is equal to pi r squared. We then, because technically pi is a number, we have to divide both sides by pi. Now, we could have technically done this all in one step and divided by 4 pi, but if that is a hard concept for you to grasp, we just did it one at a time. This here, okay, so we divided it by 4, and then we divide by pi is equal to 71.6. So wrong color. 71.6 is equal to r squared. We then have to, that's okay, square root. Okay, so I'm going to put the 2 there because when we go to use volume, we're going to need a different type of root. Excuse me. The radius of this, so we find the square root of 71, 8.46. So our radius is 8.46 centimeters. Okay? 8.46 centimeters. Now, in terms of space, this is taking up, it looks like less space than our box. Our box was 12, so it looks a little wider. The radius is only halfway, though, if you guys remember that. Our radius is only halfway through the sphere, so we would double this to find out the actual diameter of our sphere. So to find out our volume and to compare them, we need the volume formula for a sphere. Okay, volume of a sphere is it 4 over 3? Pi r cubed. Is that how they've written it for you guys? How have they written it?
Yeah.
They just put it all over 3. Okay, yeah. That's better. This is our radius. It's pretty straightforward. We're just plugging in our value for radius to find out our volume. So our volume is equal to 4 over 3 times pi times 8.46 cubed. This will give us a relatively large number. We're going to be able to do this all in one step on a calculator, I think. So 8.46, and I'm going to leave this to be as accurate as possible, even though I screwed it up last time. We cube it, then we multiply by pi, gives us, and then we need to multiply by 4 over 3. So I need to multiply by bracket 4 divided by 3, end bracket. Okay, so it's that number. Did I say divided? Times 4 divided by 3. Yeah, 1.3. It's equal to 2,538.8. 2,538.8 centimeters cubed. If you guys look at the difference in volume, it's immense. This holds a lot more space under the exact same constraint. I used the exact same material and was able to hold quite a bit more volume than if I built that cube. Bless you.